Let's solve the problem in mechanics. A typical problem in mechanics usually does not merely involve a single body under the action of a given force. More often, we will need to consider an assembly of different bodies exerting force on each other. Now, we shall solve few problems using a general set of rules which can be followed to solve any problem related to this chapter. Example 1. Two bodies of mass m1 and m2 are connected by a light string given over a smooth pulley at the end of the incline. The mass m1 lies on the incline and m2 hangs vertically. The system inclined and two masses are at rest. Find the angle of inclination and the force exerted by the inclined plane on the body of mass m1 in terms of m1 and m2. Given acceleration due to gravity equals to g meter per second square. Rule 1. Draw the diagram showing schematically the various parts of the assembly of the bodies, the links and the supports. See the inclined plane with a light pulley at the end and the two masses m1 and m2 connected by a string. Rule 2. Choose a convenient part of the assembly as one system. We consider the following system: inclined plane plus mass m1. Draw the separate diagram which shows the system and all the forces on the system by the remaining part of the assembly. Include also the forces on the system by other agencies. Do not include force on the environment by the system. Here, N equals to normal force between m1 and inclined plane. Mg equals to gravitational force on block of mass m1. Rule 4. Include information about the forces that are either given or you are sure. Example, the direction of tension. Rest should be treated as unknown to be determined using laws of motion. Now, by using Newton's laws of motion, for doing so, we need to resolve all the forces in two mutual perpendicular directions. Let us choose the following coordinate system. Resolving force in x dash and y dash direction. Since m1 is stationary, acceleration equals to 0. Using Newton's third law of motion, sigma f dash x equals to 0 and sigma y dash equals to 0, or t minus m1g sin theta equals to 0 and n minus m1g cos theta equals to 0. This implies t equals to m1g sin theta and n equals to m1g cos theta. Rule 5. If needed, follow the same procedure for another choice of a system. Since we need to eliminate theta from equation 1 and second, we choose another system, m2. Drawing its FBD, it experiences downward force m2g and upward force tension T. Since m2 is also stationary, sigma fy dash equals to 0 or t minus m2g equals to 0 or t equals to m2g. Using t equals to m1g sin theta and t equals to m2g, m1g sin theta equals to m2g. So, theta equals to sin inverse m2 by n1. Now, we know that sin square theta plus cos square theta equals to 1 and cos square theta equals to 1 minus sin square theta. Substituting sin square theta equals to m2 square upon m1 square in this equation, we get cos square theta equals to 1 minus m2 square upon m1 square. So, cos theta equals to under root of 1 minus m2 by n1 whole square. Again, using equations t equals to m1g sin theta, n equals to m1g cos theta, t equals to m2g sin theta equals to m2 by m1, theta equals to sine inverse m2 by n1, cos theta equals to under root of 1 minus m2 by m1 whole square, t equals to m2g, and normal equals to m1g under root of 1 minus m2 by m1 whole square.